So let's finish this, because you know we can actually finish this probably right now and have this entire thing be two films. Okay? So that's the big thing with the central limit theorem. What we need now is we need to have some symbols here. Let's see, where did the symbols go? Okay, so if you have proportions, if you take a sample and you find a proportion, like say, I say, okay, what's the, I'm going to pull from a deck of cards 30 times, I want to find the proportion of kings that I get, okay? And I get, success would be king, failure would be not king, and that proportion, success over opportunity. Out of those 30 cards that I got, how many kings did I get? Say that I got 4 out of those 30 cards. That would be my sample proportion, okay? And what I would do is I could create a whole bunch of proportions, 4 out of 30, and then do it again, and blah, 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 and I create that distribution, okay? But this right here is my sample proportion. That has a symbol. That symbol is p hat. P hat is my sample proportion. And think about this, we've done this before because we've talked about means, and we have a sample mean. A sample mean is x bar. It would be much more convenient if this was like p bar, because that would be like sample proportion, sample mean. Here this is sample proportion is p hat, where the other thing we have is y hat, which is predicted, and that doesn't really make sense, but then again, no one is consistent with symbols and statistics. So this is a sample proportion, okay? So then what happens if I take a whole bunch of proportions, okay? Like this. I take a whole bunch of proportions and I get values and I go boop, ba-doop, 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 ba-doop. There's my number of kings that I got, and I get that. That is my sample proportion, okay? And then here's what's interesting. If I do this, okay, and I take and I look at the mean of this, the center of this distribution, the center of my sampling distribution, just like with the means, the center of this is going to be the center of the population distribution as well. And what I would say with this is that the center of my sampling distribution, and I write that, the center of my the mean of my sampling distribution would be written like this. Mu, the mean of my sampling distribution. And it turns out that just like with what we saw with that group of means, this is equal to, and then we use the letter P, it's not a capital P, it's just a P. This is equal to the population proportion. So this is the population proportion. This is the sampling proportion mean, and then we have p hat, which is the sample value itself. That's your sample proportion. Then we take all those and we create a distribution, and we have the mean of that, and we get that, okay? So it turns out that this is going to be equal to the population mean. Now, the other thing that if we talk about this, and we talk about the mean of this, and if we talk about the shape of this distribution, it's going to be relatively symmetrical. And its mean is going to be here. The other thing we need to talk about is shape, center, and spread. Standard deviation. What's the standard deviation going to be? This is binomial. And since it's binomial, distribution, or standard deviation for binomial distribution is n times p times 1 minus p. Okay? Just like standard deviate, or just like mean for a binomial situation is NP, expected value. Okay? Which is how many am I going to get correct? N times the proportion, N times P. But if I want to turn this into proportion because it's a percentage, okay, I would divide that by N and I would get P, which ends up being the population proportion, the center of the distribution, because it's listed as a percentage. If I'm going to divide this by N because this is proportional, and I'm looking at this and I'm saying, oh look, these are percent. So therefore, as percents or proportion, I need to have these values in percent. I divided the mean by N to make this into percent. I'm going to take this, I'm going to divide it by N as well to turn it into a percent. And in order to bring this into the square root, I would have to square this. So this would end up being the square root of N times P times 1 minus P over N squared, to bring it into the big square root, and then the square and the N cancel, and you get the square root of P times 1 minus P over N. This is a standard deviation of the sampling proportion. This is the mean of the sampling proportion. Now, what's interesting is this. When we looked at this thing here, okay, this thing here, and we did this, and we said, oh, this is narrower. How much narrower is it? It's actually narrower by the square root of n. If I take the standard deviation here and I divide it by the square root of the sample size, that's how much smaller that is. And that's exactly what happened there, is we divided by kind of the square root of n, and it became, I've got 5, this is 2.25, my sample size was 5, the square root of 5 is 2 something, 5 divided by 2 something, 2.25. So you're dividing actually by the square root of n in that standard deviation, making it that much smaller. Alright, so let's bring this back here because we want to try and finish this up here quickly. Okay, now we can do the same thing for the means, and for the means, we've got this here, okay? So if I have a sample mean is this. What if I have a whole bunch of means? That mean of that sampling distribution, which was, this is annoying, which is this thing right here. What's this mean called? It's the sampling distribution mean. What does it look like? It looks like this as a symbol. It's the mean of the sample means. Just like the mean of the p hats, this is the mean of the x bars. And how much does the standard deviation change? Well, it was the standard deviation of the population, but it was smaller. How much smaller? It was the square root of n smaller. Okay? So that's what we need to talk about there. Now, in order for me to do this, in order for me to talk about these things, I need to have certain conditions that are met for this to work. Okay? And these conditions are that I need to have randomness so that I'm saying that one thing does not influence the other. Okay? I need to have each sample be independent of the other sample. I need to have randomness. Okay? This statement here of independence. I also need to have this. But what this means is this. My sample has to be less than 10% of the population. Because if I have a sample that's too big, then what happens is I could have too much of one group in my sample, and therefore I'm going to throw off what I can select. So I need to have a sample that is not too big. I also need to have a sample that is big enough. And how do I determine that? Well, if I have proportional values, if I have a binomial situation, then what I have to have is that n times p, which is the number of successes, has to be greater than 10. And n times 1 minus p, the number of failures, also has to be greater than 10. And what that means is I need to have enough successes, enough values from the mean or success up, and enough values from the mean or success down, so that I can have a symmetrical distribution. If I don't, I'm going to have a skewed distribution. So both of these have to be bigger than 10. Some people say it's 5, but we're going to go with 10. Now what happens if I have means? I don't have n times p, I just have like x bar. How can that be greater than 10? And n times x bar, that doesn't make any sense. And the logic with that is, you're just going to have to rationalize that. Okay? If you've got means, kind of the thought is if you've got a sample size of 15 or more, you're probably going to be okay. When we do things later, we'll sit there and say, oh, you know what, we'll actually make it work just for any sample size. But if our sample size is 15 or bigger, we're going to be okay. And, no, okay, so then we have something called the standard error. And what's the standard error? Standard error is say that I don't know what the population value is, because all I have is a sample. Say I'm given a data, I have a population and I don't know what it is, but I want to guess what it is, and I want to find out what the mean is, or I want to find out what the proportion of successes should be. So I grab an entire group and I sit there and say, okay, let me do some samples. And when I do that, what's going to happen is that my standard deviation, which is the square root of p times 1 minus p over n for a sampling situation, is based off the population proportion. But I might not know what that is. And if I don't know what that is, I can't create the standard deviation. So what we have is we have something called the standard error. And what the standard error means is this. It means I don't know what P is, so I'm going to use the next best thing. And the next best thing to P, don't go there, the next best thing to P is P hat. So instead of having P times 1 minus P over N, I would have P hat times 1 minus P hat over N. And I sit there and say, I'm going to use that as my standard deviation. But it's probably going to be wrong because my sample proportion is not necessarily, now this is just one sample, this sample value is not necessarily going to be the true population value. So it's probably going to be wrong. But it should be, fairly close, I would guess. I mean, sampling error is going to occur, but, it's the best thing I got to go. So instead of calling it standard deviation, we call it the standard error. And for this situation, it's the standard error of P hat. Okay? Now, when we talk about means, what I have is I did have the standard deviation of the population divided by the square root of the sample size. Maybe I don't know the standard deviation of the population. All I have is my sample values. So what do I use in place of this? And the answer is, what I'll use is I will use what I have. And I don't have the standard deviation of the population. I have my standard deviation of the sample. And my sample might be wrong, but I'll use it anyhow, and that would be my standard error for means. And standard error for means is written as a standard error for means. And wow, that just sets us up for like a really bad stats joke, as in like, oh, guess what I learned in AP Stats? I learned all about the standard error of X bar. That's chapter 18 in a nutshell. There you go.